Okay, so the title of this episode is the dot product. This is also called the scalar product. And what it is a product. It's also called an inner product, by the way, if you come across that, inner product. And what it is a product between two vectors. And it's denoted by a dot, hence it's called the dot product. How do I define it? So the definition is the following. Since we started things from the geometric point of view, I'm going to continue with that line. So I'm going to define it geometrically first. So the definition is going to be, take the length of A, multiply it by the length of B, and then multiply it by cosine of alpha, where alpha is the angle between A and B. And remember that here and almost everywhere, when I say the angle between A and B, I mean this angle, where A and B start from the same point. Okay, so that's the definition. Do you agree that the objects that I'm multiplying are vectors? Do you agree that the result, that what I'm getting here, is a scalar? This is a scalar, it's the length of a vector. This is a scalar, it's the length of a vector. And this is a scalar, it's cosine of an angle. Okay, so that's why it's called the scalar product. Okay, it's a weird thing if you haven't encountered things like this before. You're multiplying two things and getting something in a different world. Okay? If multiplications that you've met so far were multiplications of numbers, then usually you multiply two numbers, you get a number, right? Here we're multiplying two vectors and we're getting a scalar. Okay? So the first thing we have to do before we move any bit forward is to erase the disk. Okay? Forget everything you knew about products ever, and we're going to start building from scratch. Okay? Is it true, for example, that A times B is the same as B times A? We have to figure it out. Is it true that A times B times C equals the same as A times B times C, where you interchange the location of the parentheses? We're going to have to figure it out. That one's not just going to be false, it's not going to even make sense. Okay, we'll talk about it. Okay, so you have to be careful. It's very tempting to say, hey, this is multiplication, I know multiplication, and to just move forward with everything you know. You're going to get a lot of nonsense. Okay, so careful. Okay, so let's see what we can say about this. So the first thing that we're going to say is some properties. The first observation, which is very useful, so property number one, two vectors are perpendicular, that's what this notation stands for, they're in 90 degrees to each other, if and only if, you know this symbol, right? If and only if, what? So when are two vectors, here are two vectors, when are they perpendicular? When the angle is what? 90 degrees, right? Well, the angle is 90 degrees. What does it mean about the cosine of the angle? 0. So two vectors are perpendicular if and only if the angle between them is 0. But if the angle is 0, if the angle is 90 degrees, the cosine is 0. So if the angle is 90 degrees, if they're perpendicular, the cosine is 0, so what's the dot product going to be? 0. So that's this statement. If and only if A dot B is 0. So the dot product is 0 is kind of a tool for identifying perpendicular vectors. Is this clear? Okay, you can call it a theorem, but we just proved it. We just said the proof. Everybody good? Okay, so that's a first observation. Another observation, again, this is, it plays an important role, but for us we're going to just call it a property or an observation. A dot B is the product. Make sure, by the way, that when you do A dot B, you make the dot fat and visible. Okay? So it's clear that it's there. So A dot B is the product of the length of A. Well, that's obvious because that's how we defined it, the length of A, times the length of the projection, the projection of B onto A. I'm going to explain this. The length of the projection of B on A. So what's the projection of B on A, and why is this statement true? So let's take here, let's say this is B, and let's say this is A. And the projection of B on A is just, take a 90 degrees angle here, and this thing in purple, this vector here, this is called the projection of B on A. Is that clear? That's what it's called. Okay? You can imagine somebody coming with a big light and lighting from above. That's the shadow that B is going to leave on A. Do you see that? Okay? Clear? Everybody good? So this is called the projection of B on A. Now what's the length of this thing? This angle is alpha. Do you agree? And let's call this thing temporarily, let's call it x. Just temporarily. These are vectors, by the way. Okay, so let's call it temporarily x. I didn't mean for it to be a small x. X. That's the purple one. So what's the length of x? So do you agree that cosine of alpha is the length of x divided by the length of b? Right, in this right triangle. So it's the length of x divided by the length of b. Does everybody see that? Say yes, come on. Thank you, thank you. Therefore, the length of x equals the length of b times cosine of alpha. Do you agree? So the length of the projection of b on A is b cosine alpha. Hence, back to the previous board, A dot B, which is A times B cosine alpha, is the length of A times the length of the projection of B on A. Clear? Okay, so that's this remark. Now let's write, continue these properties as a list of some more algebraic-like properties. So here are some more properties. So A dot B equals B dot A. This is in fact true. Okay, so the dot product is commutative. It doesn't matter which one you multiply by which one. Why is this true? How would the proof go? Very easy. A dot B is the length of A, the length of B, times cosine the angle, right? B dot A is the length of B, the length of A, times cosine the angle, and it's the same angle, right? Between B and A and between A and B. So they're the same. Do you agree? Okay, so this is easy. Number 4, more properties. Distributivity with respect to vector addition. A times B plus C equals A times B, let's say dot. A dot B plus A dot C. Okay? This requires proof, and the proof is not something you just quickly write down. In order to formally prove this, you have to argue a bit more delicate argument that has to do with these projections business. Okay, and I'm not going to do it. I'm going to skip it. Okay, but nevertheless, this statement is true. So we have the distributivity. Number 5, scalars move around freely with respect to this multiplication. So if I take a scalar m and multiply it by a dot b, that's the same as taking m times a and multiplying that by b, and that's the same as taking a and multiplying that by mb. Now note that there are 3 different multiplications showing up here. Do you see 3 different multiplications? Well, obviously you see one, here it is. You probably see the other one, right? This is the product of a scalar times a vector, which we defined previously. There's a third one here, over here. This is just the regular good old product of 2 scalars. A dot b is a scalar, m is a scalar. This is just product of 2 numbers in R. Do you see that? So do you see that there are 3 different products hiding here? 1, the dot product between 2 vectors. 2, a product of scalars. And 3, a product of a scalar and a vector. Okay? Delicate. You just have to pay attention when you do things and not assume anything for granted. Okay? So this is true. This is not easy to prove. You just have to spell out the definition of what is a dot b. Length of a, length of b, cosine the angle, and then see that the m moves around. For positive m's, it's a bit easier. For negative m's, it's a bit trickier, but it's still a line and a half. Number 6, this one's going to look a bit silly, but it's so useful that it deserves a statement of its own. So what is a dot a? A dot a, by definition, is the length of a times the length of a times cosine the angle between a and itself. What's the angle between a and itself? 0. What's cosine of 0? 1. So that's the proof of this. Did everybody follow that, or do you want me to say that again? Everybody good? So a dot a, by definition of the dot product, is the length of a times the length of a, that's the length of a squared, times cosine of the angle between a and itself, which is 0, hence the cosine is 1. Clear? And this is very useful. We're just going to use it a lot, so I wrote it. Okay, some more properties. Here's another one that is very trivial to prove in this context, after having defined it geometrically. In general, this is a theorem that shows up in many, many, many different cases that seem totally unrelated and is sometimes not easy to prove and is always useful. And it's called the Cauchy-Schwarz inequality. Cauchy, you know Cauchy from Calc 1, right? This is the daddy of epsilon. You saw the definition of a limit, right? He's one of the parents, Weierstrass being the other. So Cauchy-Schwarz inequality says the following in this context. It says that if you take a dot b and take its length, take its absolute value, right? A dot b is a scalar. So when I do these 2 lines around it, it's the absolute value of that scalar. It's not a length, because this is not a vector. Clear? And this is always less than or equal to the length of A multiplied by the length of B. Why is this true? Let's prove it in our heads very easily. What is A dot B? It's the length of A times the length of B times cosine of alpha. Cosine of alpha, no matter what alpha is always less than or equal to 1. Do you agree? So the length of so A dot B is always less than or equal to AB cosine alpha is less than or equal to 1. Clear? Do you agree that here this is for free? It doesn't even pay to write down the proof. It's so obvious. Good? Okay, so this is the Cauchy-Schwarz inequality. Let's see a few things that you would write without giving it a second thought for multiplication in general and do not hold here. Okay? For example, we had distributivity, we had commutativity. What about associativity? So you would want to write A dot B dot C equals A dot B dot C. Is this true? This is the associative law, right? So not only that it's not true, this thing is complete nonsense. Why? Because B dot C is a scalar. There's no such thing as dotting a vector in a scalar. Do you agree? So do you agree that even writing this doesn't make sense? It just doesn't make sense to write this. Do you agree? Okay. So this doesn't make sense. And in particular, this whole thing is just not. Okay? You could ask, so let me take a red and put a big X on it. Because it just doesn't make sense. Now you could take it a step forward and ask, is it true, for example, so this does make sense, so here's a little homework exercise. Is it true that if you take A is a vector, right? You could ask, what is A, B dot C? This is a scalar times a vector. That's defined. Is this the same, here's a question mark, as A dot B times C? So this is a scalar times a vector. This makes sense. This compiles. This is a legitimate question, but the question is it true? In order to prove that it's true, you somehow have to use the definitions to show that it's true. Do it. In order to prove that it's not true, you have to give a counterexample. Give 3 concrete vectors, A, B, and C, for which the left-hand side and the right-hand side are not the same. That would be saying that this is not true. Okay? So I'm not going to tell you if it's true or not. I'm leaving this one as homework. Okay? Here's another one that's not true. I just told you. I can't believe I did that. Okay, here's another one that's not true. Sorry. Suppose you know that A dot B equals A dot C. Okay, suppose you know this. Does it follow, what would you want to say? That B equals C, right? You would want to cancel out this A, right? You do that freely in numbers. If 3x equals 3y, then x equals y, right? You wouldn't give it a second thought. Is this true? Okay, so the answer, no, it's not true. Not true. And since we're out of time, do I want to leave this as homework as well? Well, let me just show you real quick. So take, for example, take this to be A, this to be B, and this to be C. They don't have to be the same length. Okay? So A dot B is what? 0. They're perpendicular, right? Likewise for A dot C, they're also 0. So A dot B equals A dot C for this picture. Do you agree? However, B is not the same as C. They're not the same length and they're not even in the same direction. Do you agree? Okay, so this is a counter example. Counter example. Clear? Okay, there are a few more properties that I want to mention. We'll do it next time. And what you do, even up to this point, you have to be very careful that this is a new notion. It's a new kind of multiplication. Take nothing for granted. Okay? So we're going to discuss a bit more properties next time, including the algebraic approach, how we do scalar product in coordinates. That's not going to be hard. And then we're going to learn yet another kind of multiplication, a multiplication of vectors that gives a vector. That would be next time.